Okay, so Lecture 4, the particular solution. So, what effect does the forcing function f have on the solution? Remember, we're working with this equation 1, 1, this guy, and it's got the left-hand side with the time derivatives of the output y. The right-hand side is the forcing function. How might we solve for the effect of the forcing function, called the particular solution? One answer to the latter question will be given in this lecture using the method of undetermined coefficients. Hopefully that rings a bell. If it doesn't, could be trouble, but do your best. Before we turn to this method, please recognize that other methods, such as the method of variation or Laplace transforms, apply to more general forms of forcing f, although the integrals that accompany each may be unknown. So we're only going to be considering a sort of limited class of forcing functions. So that's important to keep in mind. When choosing the method of undetermined coefficients, we limit the scope of applicability to systems subjected to forcing functions that are complex exponentials, which, as we saw in the last lecture, include sinusoids and regular real exponentials as well, or polynomials. The principle of superposition, discussed in the mechatronics course, we won't cover it in the primer, allows us to construct solutions for linear systems subject to linear combinations of complex exponentials and polynomials. So we'll use this very powerful principle of superposition. Now we'll feel like we're very limited to, you can only have forcing functions that are very simple, but we'll increase complexity as we proceed. So in this primer, though, they'll be rather simple, and we'll build up our repertoire as we go. So, method of undetermined coefficients. The method is 3 steps. Always 3, right? You always have 3 steps. Based on the form of the forcing function, propose an appropriate solution that includes undetermined coefficients, hence the name of the method. Being careful to propose a solution linearly independent from the homogeneous solution. We'll return to that phrase, okay? Step 2. Substitute this proposed solution into the ODE. Okay, just plug it in, like as if it's a solution. We're proposing it. We don't know if it is a solution. We have to plug it in, and then we have to check. So some people call this first step sort of proposing a solution. They say guess. I prefer the term propose. Kind of snob that way. Okay, so 3, determine the undetermined coefficients by solving the algebraic system of equations that results from equating terms on each side of the equation. So we determine the undetermined coefficients in this method as well. So there. So they don't end undetermined, they start undetermined, and we find them. So if there is, in fact, a solution in step 3 for these undetermined coefficients, that is a solution for the algebraic system that results from plugging in our proposed solution and equating all of the coefficients, our proposed solution is our particular solution. So we proposed it, and then the approval is, there are coefficients, we can determine what they are, that give us a solution. Okay, so we're testing not only to see if our proposed solution is a solution, we're also trying to figure out what those coefficients are, those undetermined coefficients are, through the method. So we get 2 things with one method. So our proposed solution is now our particular solution with coefficients determined. However, if there is no solution, so as you know, if you try to solve a system of algebraic equations, there are certain situations that arise where there is no solution. And if that happens, then the proposed solution is not our particular solution. So we got denied. We got shut down. We go home sad. Okay. But as you'll see, we'll virtually never propose the wrong solution as long as you go through this primer, because I'm giving you the inside scoop here. So, 4-2. I realize that you don't all know me yet, so hopefully my humor is coming through and it's not just weird. Well, it's probably both. Okay, 4-2. Some suggested solution proposals. So how can one propose a solution? There are actually no clear answers other than be clever or just use known solutions. It's not very satisfying. So as remarkably unsatisfying as this is, we can still rejoice in being let off the hook, since we are certainly not clever. As mentioned above, this method only really works if the forcing function is a complex exponential or a polynomial. But this can be extended using superposition to a large class of problems of interest. So we'll see that in mechatronics. Table 4.1 is provided as a guide, but it essentially boils down to this. If f, so the forcing function, is a complex exponential, propose that the particular solution, yp, is a complex exponential with undetermined coefficients. If f is a polynomial, propose that y of p is a polynomial. Okay. Here's our table 4.1. So it's sort of broken down into different variants of complex exponentials and polynomials. And so if you look here, you have your forcing function in the first column. The corresponding particular solution we should propose. Great. So as long as we correctly identify the forcing function, we should have no trouble identifying what we should propose as our particular solution. Notice that we have all of these k's in here. So first of all, these k's are just anything. So it could be like 5 or 10. It doesn't matter what they are. They don't actually show up in the proposed solution explicitly. It matters, like if you multiply this by 5, that'll change what the big k's are over here, but we don't actually have to use little k in the proposed solution at all. It just comes along for free. The proposed particular solutions have these undetermined coefficients, k1, k2, k3, etc. And we're going to plug these proposed solutions into the original ODE, with f being whatever it is, so the forcing function, the right-hand side being whatever it is, and then we just solve for what those k's need to be for that to be true. And hopefully there is a set of k's for that to be true. That's not necessarily the case, but as long as we've stuck to this table, we should be fine. If not, there's this very small chance that I screwed up the table. Shouldn't be your first place to go, though. Probably you that messed up. Just saying statistically here, I mess up a lot, but I feel like students, you guys mess up more than me. I'm not trying to say that means anything. It means that I feel cool, is really what it means. So, test values. So we're going to talk about test values in just a moment. So just notice that's the third column here. And it's pretty simple. It's zeros, lambda, so whatever the lambda is that was in the exponential forcing function, and j omega, so whatever the omega was from the forcing function, j here, and throughout, and I think I failed to mention this before, I, j, and we use these as indices a lot too, so you have to just look at the context, but they're both used throughout mathematics and engineering as the square root of -1, the imaginary number. We're going to prefer j in this course, mostly because we will be, in the mechatronics course that follows on to this, we'll be using I for current a lot, so we don't want to use it for the imaginary number. although we also use I and J for indices all the time too. So you just have to recognize the context, especially when it shows up with an omega, it shows up in an exponential. Think probably is going to be the complex or the imaginary number. Okay, so I'll be using J throughout. I won't use I at all. Okay, excellent. Good. So 4-2. No, we did 4-2. So those were the suggested solution proposals. So that was the table. The parenthetical caveat. The only caveat here is the parenthetical warning from the three-step method about choosing a linearly independent solution. The one I told you we would return to. This guy right here. Okay. So it says, being careful to propose a solution linearly independent of the homogeneous solution. Which means that although the homogeneous solution doesn't explicitly enter into our method here, it does mean that we have to have it first. So you have to do the homogeneous solution first, and then you can get the particular solution. It's sort of an edge case. Sometimes, most of the time you'll be fine if you don't do that and you don't check this, but it's good to check in case you have this occur. So this result is a result of a theorem we have not considered here, but suffice it to say that in order for our general solution to simply be the sum of the homogeneous and particular solutions, which is what we want, as we will propose in the next lecture, these two must be linearly independent. I fixed this, but I must have updated it. Must be linearly independent. We will not only skip the details of why this is the case, but also the details of how to deal with it, opting instead for a simple recipe. So I'm not teaching you how to deal with it in general, but in the cases that we're giving you in this table, so in the method of undetermined coefficients a la this table, I will show you how to deal with it. And you can use these test values to do that. So the test values of the third column are to test whether or not the particular solution is a component of the homogeneous solution. If the test value is equal to any root of the characteristic equation of multiplicity mu, then the proposed solution must be multiplied by t to the mu. I think that it's pretty easy to see why we're doing this multiplication. It's a little harder to talk about it in general, but if you've got this so for instance, in this case, take this row. If you have k e to the j omega t as your proposed solution, so or k1 e to the j omega t as your proposed solution, you test to see if j omega is in the homogeneous solution. If it is, then you have to put a t here. If there are two of them, if there's one of them, then you have to do. If there's only one of them, you have to put a t. If there are two of them, you have to put a t squared, etc. And this is actually, you can see this as being sort of the next index of our general formula for the homogeneous solution that showed up before. So when our particular solution is one of the homogeneous solutions, we essentially add one more term with a t, one more t in it. So it doesn't happen a lot, but it's important to recognize that can happen, and you should be aware of it and test for it. So use this third column, the test values over here, to make sure that you're okay. So excellent. Great. So that's the whole method, the method of undetermined coefficients, to find the particular solution. So let's do an example. A particular solution. So find the particular solution for the equation. We're going to use the same equation we used before, but we're going to actually specify a non-zero forcing function, f, with f of t equals a cosine omega t, where a is some real number and omega is 5 radians per second. Now, this is something that I do a lot. I don't always give you a number for a parameter. So in this case, I just said A, some number times cosine omega t. So carry that A around in all of our calculations, which is a bit annoying, but also once you do it, it actually, it's easier than writing a bunch of numbers, in fact, and it's good practice, even if you have numbers from the beginning of a problem, to just put in symbols instead. When you get to the end, you get to see which symbols, which parameters affect the solution and how. So that's a really important thing to get used to now. Start practicing that now. I do it a lot in my problems, including my exam problems. So good luck. So, okay, so let's solve this. Get my handy notes. Okay, so like we mentioned a minute ago, although we aren't going to use the homogeneous solution explicitly in this particular solution, we do need to have it in the bag. And we happen to, because this is the same problem I gave in the other lecture, where we already found the homogeneous solution. And what we're really going to test, remember those test values, we're going to test to see if they're equal to any of the roots of the characteristic equation, any of those lambdas. So let's just rewrite our lambdas. So recall the roots of the characteristic equation. So we had lambda 1, 1, we called it, equals -4. We have lambda 2, 1 and lambda 2, 2 being equal to -3. That was our repeated root. I'll put semicolons here to make it a little bit more clear. Ooh, those look like J's. I'll put pipes. Not like from Orange is the New Black. It's different. Okay, and then lambda, I guess it was 3, 1 is equal to -2 plus J2, and lambda 4, 1 is equal to -2 minus J2. So those were our roots of the characteristic equation. And when we select from our table, we're going to need to use the corresponding test value to make sure it's not equal to one of these. Or more than one of these, right? Because we could have a double root. We already have a double root, so we could have another triple. It's not a root when it's coming from the forcing function, per se. So we have ourselves our table 4.1. The forcing function we have is this. So we need to look up this in the table. So we go back up to our table, and we see looks a lot like this row to me, right? So some constant times cosine omega t plus phi, where phi is 0. The phase in this problem that we're doing is 0. So that's what we've got. So our proposed particular solution should be this guy. K1 cosine omega t plus K2 sine omega t. Actually, it doesn't matter if phi was not 0 here, you still guess the same thing. And that's because having the cosine plus a sine gives you that phase shift in there. We'll talk more about combining cosine and sine together, and they have the same argument later on, mechatronics and whatnot. So let's use this, but we'll also need to try out our test value. So let's write it first. The omega is the same omega as from here, so it was 5 in our problem. So from table 4.1, we propose that the particular solution, yp of t, is k1 cosine omega t plus k2 sine of omega t. And after this, I'll probably start dropping these parentheses. It's something that you see a lot. It's a little bit ambiguous, the notation, when you have no parentheses here, but if you have an omega t together, it happens so frequently that you'll see it a lot, that people will drop the parentheses. So it's a matter of style. I try to be explicit at first, but then I slowly introduce leaving them off. If it's ambiguous in any way, include the parentheses. If you feel like it's not clear from context, put in the parentheses. It is a little bit risky not to put them in. We like to live life on the edge a little bit, you know. So this is our proposed solution. Let's check, though. Checking the test value, which the table said was j omega, right? So j omega is equal to j, so j is our imaginary number, right? Omega is 5 radians per second, so j5. We see that this is not equal to any of these lambdas. So we have -4, -3, -2 plus j2. This is, these two are the only two that have any imaginary at all in them. But even if this was -2 plus j5, it's not equal because there's a real part here. So there's no j5 showing up in our so there's no j5 showing up in the roots of our characteristic equation. So we're fine. So we don't have to be concerned with this sort of edge case of needing to multiply by t raised to the multiplicity of that root. We're good, I'll say. So we're good. So now, what we need to do is we need to plug this proposed solution into our original ODE, okay? So into here, which is pretty easy. I just say that, y is equal to yp, and I'll actually rewrite that explicitly. But then we have to take these derivatives, which we'll do separately. So I'll say substituting, which is, the fancier version of plugging into, plugging into our ODE. So to review, we're actually on step. So substitute the proposed solution in the ODE. We're on step 2 now. So we proposed it, we're going to substitute it in, and then we're going to have to determine the coefficients. So we say y is equal to yp. So we just essentially rewrite the differential equation. So d is the fifth. So d5 dy dt to the 5. So the fifth time derivative of y plus 14, the fourth time derivative of y, plus 81, the third time derivative of y, plus 248, the second time derivative of y, plus 408 times the first time derivative of y. Oh, what are these? I've just been doing y, but we're plugging that y is equal to yp in here. So yp, 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 yp. Maybe had to go. Okay, 20. So 288 yp equals, and then f of t. So our forcing function is just a cosine omega t. So that's our substitution, or step 2. And so we actually need to put yp that we proposed in explicitly, right? So in order to do that, it's easiest to compute the time derivatives separately. So let's actually go to the next page for this, but I'll write it here. So let's compute the time derivatives separately. So we don't want to write that out in long form. That would be really long. So let's do the first one. So dyp dt. So you just take the derivative of our yp that we proposed. So the derivative of cosine is negative sine, so negative k1 chain rule, right? So there's an omega that shows up, so cosine turns into a sine omega t, plus the other term was a sine, so it becomes cosine, right? And there's no sign change, so it's k2 omega cosine omega t. And remember, I've not put the parentheses in, but they're there, right? Okay. Let's do the second derivative of yp with respect to time. So, Niles, come on, man. Derivative of sine is cosine, so negative k1. We pick up an extra omega from the chain rule. Cosine omega t. Cosine, negative sine, right? k2 omega squared sine omega t. The third time derivative equals, so derivative of cosine is negative sine, so now we get positive again, k1 omega cubed sine now omega t. Derivative of sine is cosine. Niles, he's just being naughty. Sine is cosine omega t. Good. Now we're going to do the fourth derivative. Come on, man. Niles, come here, buddy. Come on. I don't know. So, good. Derivative of sine is cosine, so we have k1 omega to the fourth power cosine omega t. The negative becomes positive, and we've got k2 omega to the fourth sine omega t. Last one. I think Niles was just getting bored. Okay, derivative of cosine is negative sine, so negative k1 omega to the 5 sine omega t. Derivative of sine is cosine omega to the 5th cosine omega t. Oh, so you just kind of go through that methodically. Let's make sure I got that right. Plus, minus, minus, plus, 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 minus, minus, plus, plus. Good. Minus, minus, plus, plus. Looks good to me. Hopefully I did it right. It's only the internet, right? Okay. Hi, Niles. Are you going to come say hi? Come here, buddy. Come here. Do you want to come say hi? Come on. It's going to run away if I had one check. Come on, puppy. Do I have something for you? Let's see. Ooh. Do I have snacks? Can you sit? Good boy. Oh, good boy. Now you gotta come say hi. Oh, he's my buddy. So Niles, can you look over there? Can you say hello? He's like, you're so weird. Turned out, I was talking to Niles today. Turns out he's a Marxist. How many people have Marxist dogs out there? I feel like it's got to be a thing. He's been reading all this stuff. Turned him into a Marxist. Not even like just like the critical of capitalism kind of Marxist, but like he's like hardcore. Aren't you, buddy? You my little radical. Yes. Okay. So now, Niles, you just lay down. Can you sit? Sit. Good boy. This is just pretty much my life. Lay down. Lay down. Good boy. Okay. All right. So, back to business here. We've got our time derivatives of yp, so we're ready to substitute them in. But we should refrain from the temptation to write that out long form. That would be a mess. What we can do is we can recognize that there's going to be a cosine term that shows up in every one of these. There's going to be a sine term that shows up in every one of these. Similarly, on the other side of the equation, we have a cosine term, and then presumably the sine term has a coefficient of 0. So what we can do is form a system of linear equations from equating the cosine and sine terms. So we get two equations from this because the cosine coefficients have to equal the cosine coefficients on the other side. So left-hand side cosine has got to equal right-hand side cosine. Similarly, the left-hand side sine has got to equal the right-hand side sine. So that's what we've got for our system of algebraic equations from which we can determine our coefficients. So let's do just that. So we've got each term, we plug in, and then I'm going to copy this down actually so we can see it while we do the substitution because it's a little hard to see it. I'll just put that. Just put that right there. Okay. So I'll say equating cosine and sine coefficients. So let's just go term by term. So the first term is the yp, the fifth derivative, right? So let's go here first. We'll do cosine first. So we'll do the cosine coefficient. So that one, we pick this guy right here, right? K2 omega to the fifth. So K2 omega to the fifth plus 14. So then we go to the next one. We're going to do all cosines, right? So next cosine is K1 omega to the fourth, right? So K1 omega to the fourth. And then we've got the next cosine term is negative. So we have minus 81 K2 omega cubed. The next cosine term is also negative. So minus, and then we've got 248 K1 omega squared. And finally, we've got K2 omega as the first derivative. So plus 408 K2 omega, and then finally 288 YP. The cosine term was our K1 term, right? Yeah, K1. So K1 equals, the right-hand side has a cosine term with a coefficient A. So there we have our first equation. We're only going to need two, so we're good. We have two unknowns, K1 and K2. The sine equation is done very, very similarly. So we've got negative K1 omega to the fifth plus 14 K2 omega to the fourth plus 81 K1 omega cubed. And then we switch over to minus K2, so minus 248 K2 omega squared. And then up to here, we have minus 408 K1 omega, and then we have plus 288 I have an old house. It might be haunted. If so, I hope this video makes it out there so you guys can see the truth. Okay, so we have two equations which kind of look bad, all right? We have all these omegas in here. We have an A in here. We have four symbols, so does that mean we have four unknowns? No. A is a known, right? It's some real number. It's a symbol. We can solve for K1 and K2 in terms of A. Similarly, omega, we actually know is equal to 5. That was given in the problem. So we haven't plugged it in. At this point, we should still not plug it in. We should solve this system of two equations, two unknowns. It's a linear system of two equations and two unknowns. It's actually not bad. We could use elimination. We could use substitution. We could use a sort of matrix method. You guys have been solving these systems forever. Probably really tired of it at this point, I would guess. So let's skip that boring part because, frankly, who wants to do that? So, solve the linear system however you feel like it. Solve one equation for K1, plug it into the other equation. Solve for K2 in the other equation. Back substitute into the first equation, and then you've got yourself a solution, for instance. I'm going to write, this is the actual expression in terms of omega is kind of long. So I'm just going to plug in omega equals 5 for K1. And this is 82.00 approximately, because this is a rounded off number here, times, I'll write it like this, times 10 to the negative 6. So that's the coefficient that comes from omega, right? You plugged omega in, got this times A. So whatever A is, we couldn't plug that in because that was something that wasn't given in the problem, other than to say it's a real number. So that's K1. K2 is similar. It is negative 159.4 times 10 to the negative 6A. Cool. So, since there was a solution, that means our particular solution that we proposed is actually the one that we proposed is actually our particular solution. So this is good. And we've determined the coefficients along the way. So we've determined the undetermined coefficients. Now I guess they're the determined coefficients. It didn't seem like they were really that motivated. I don't know. Should be positive. So that's how you do the particular solution. And I picked, frankly, a pretty involved problem. This was fifth order. We had to take 5 derivatives. And then we had some symbols in there that we didn't have defined as in terms of numbers. So we had to carry them along with us. And we did it with omega too, right up until the bitter end. We should have written down the expression with omega. It was just a little messy, so I didn't want to make it look intimidating. So I left that off. But yeah, all pretty straightforward stuff, and we have a particular solution. It all started with having a good value from the table, our good proposed solution from the table. And, I didn't steer you wrong. These are good. So when you plug them in, you should be fine when you get to the end. Make sure you do your test value and go forth from there. And then you just have to solve a system of linear equations for the unknowns, which in most problems, it's just going to be, at most 2. You don't see a lot of polynomial forcing functions, so you're mostly going to be in this region here. So 1 or 2 undetermined coefficients, which means there's going to be 1 or 2 equations to solve simultaneously for the coefficients, the undetermined coefficients, K1 and K2. So the exercises for this are similar to those in the previous section, but they are a little bit different. I give you forcing functions. So in these forcing functions, you plug them in, so you're going to have to find homogeneous solutions first, right? So don't forget to do that. I probably am going to put at least one in there where you have to use the test value, right? So I also have not solutions, but answers at the end in Appendix A. So look at those, but also, it's not for a grade. It's just for, yourself. It's only your life. So lots of cliches I could throw at you now. In any case, that's all I'm going to say for that. Next time we're going to finish it up, Lecture 5, with the general and specific solutions. We're going to put these two, the homogeneous and the particular, together. We're going to have to solve for a couple more coefficients, and then we'll be good. All right. Till next time.